The global carbon cycle is the one cycle to which we probably pay the most attention. Carbon has both a direct role in the productivity of the biosphere as well as climate. Here, we'll examine an overview of the global carbon cycle, then turn to how humans have influenced the carbon cycle. Photosynthetic uptake of carbon from the atmosphere and ocean provides the fuel for most biological processes. This, in a nutshell, nails down why carbon is so important. We think of carbon as being the main factor that determines biological processes. But in addition to this, we also recognize that carbon is important for climate. And we know that carbon dioxide in the atmosphere, for example, as well as methane, are important constituents in regulating the temperature of the atmosphere. Earlier, we had covered the basics of the carbon cycle, from photosynthesis to respiration to other factors like movement and storage of carbon in different pools. That was for an ecosystem, and the question now is, how does that play out globally? So if we start with the pools, for example, if we look on a global scale, what are the different pools of carbon and what are their relative abundances? In short, where's most of the carbon? This is figure 14.5, and it looks pretty similar to earlier figure that looked at water, but this figure focuses on carbon. And we're going to take a look at some of the pools and later fluxes of carbon. In each one of these boxes, it'll tell you what the pool is, and then it'll have a number in black. And that number represents the amount of carbon in that pool. The units on this are petagrams. Petagrams of carbon. And a petagram is approximately 10 to the 15th grams. So that's a large number. And I'm not going to talk about these units, but all of these units here are petagrams. And that's the typical unit that we use for understanding carbon on the global scale. So let's take a look at, in these white boxes, we're going to look at the black numbers, and we're going to just compare their size. Later, there'll be some fluxes that we'll look at, and we'll look at the anthropogenic contribution, which is shown in red here. But for now, I just want to focus in on these numbers. So if we look for the biggest number, there's 37,000 in the deep water, 900 in surface waters, 1,500 in soils, 650 for vegetation. Wetland soils is 450, 1,500 for permafrost. Rocks is a really big number, 60 times 10 to the 6th. Sediments, 150. Biota, just 3. And that's ocean or aquatic biota. So what are the biggest pools of carbon? Rocks hold a lot of carbon, and there's a lot of calcium carbonate, a lot of limestone in the world, and a lot of the carbon is actually stored in inorganic form in rocks. After that, we're into deep water. And the deep water of the ocean holds a tremendous amount of carbon, 37,000 petagrams. By comparison, when we look at soils are roughly 1,500, and compare that to vegetation, which is 650. Permafrost is also 1,500. So permafrost is permanently frozen soils, generally in northern latitudes, and there's a tremendous amount of carbon that's been stored in permafrost. So aquatic systems, 37,000 and 900 for deep and surface waters. For terrestrial systems, we've got 1,500 petagrams and 1,500 petagrams in permafrost and in soils. Vegetation is roughly half, it's less than half, but roughly half of soils. So there's half as much carbon in vegetation as there are in soils, not accounting for frozen soils. The atmosphere is 762 petagrams. So there's a similar amount of carbon in vegetation as atmosphere, and twice as much carbon in soils as there is in the atmosphere. Now, wetland soils is not quite as much, but there's a significant amount of carbon stored in peat and these highly organic sediments that we find in wetland soils. So if we ask where's most of the carbon in the world, as far as pools are concerned, it's mostly in rocks, but then once we think about the biosphere, deep water, and then after that we've got soils and permafrost. So a lot of that carbon in the world is being stored in soils, is being stored in waters, and a fair amount is being stored in vegetation, and roughly a similar amount in vegetation as there is in the atmosphere. So it's important to know that there's twice as much carbon in the soils as compared to atmosphere or vegetation. So the soils are an important repository for carbon at the global scale. In addition, permafrost is important too. Permafrost is what's considered to be permanently frozen soils or perennially frozen soils. And these soils had a lot of carbon before they were frozen, and now they store almost as much carbon as we have in other soils of the entire world. When we take a look at fluxes, so pools are one thing, but fluxes, how much carbon is exchanging between different pools? In this case, we're going to take a look at different numbers here, and they're numbers associated with the arrows. So we're talking petagrams of carbon per year for units here. And let's just take a look at some of these fluxes. So into and out of the ocean. Out of the ocean 91, into the ocean 92, and this is out of balance because on a net basis, oceans have been absorbing a large amount of carbon each year. But we're talking somewhere on the order of 90 petagrams for the oceans. How does that compare to vegetation? Net primary productivity is thought of as being 60 petagrams of carbon. Respiration, heterotrophic respiration, 56. So again, not quite in balance because net primary productivity, 60 petagrams of carbon, 60 petagrams of carbon moving from vegetation to soils, and that's somewhere on the order of 2/3 of what we're seeing for oceanic flux. Now, fluxes to the atmosphere. River outgassing and weathering of rocks, pretty small numbers. Fires, we're at 4 petagrams, 0.1 for cement. Fossil fuels, 7.6. Land use change, 1.5. And then we've got heterotrophic respiration again, was at 56. So fires, that's a lot of carbon leaving the terrestrial biosphere into the atmosphere. So it's almost 10% of what we see for heterotrophic respiration. Not quite, but almost. Fossil fuel use, 7.6. So if you look at all of the respiration in the world, and then look at fossil fuel use, fossil fuel burning, for example, that more than 10% fossil fuel CO2 emissions are more than 10% of all the respiration in the world. And now as a basis, 7.6 versus 650, it's equivalent to somewhere on the order of 1% of all the carbon in vegetation is being combusted, or equivalent thereof is being combusted from our fossil fuel use. So it's a pretty significant flux. And here's our atmosphere, which is really absorbing a lot of these fluxes. Oceans, and its exchanges with oceans, river outgassing, fires, fossil fuels, land use changes, things like that. So as far as fluxes are concerned, huge fluxes associated with the ocean, but more or less in balance. And then we've got large fluxes, so we have to think about fires and fossil fuel emission, as well as heterotrophic respiration, as far as being the major components of sources of carbon to the atmosphere. Now, we don't talk too much about oceans, but it's important to recognize that for ocean fluxes, the flux from shallow to deep is important. I'll go back for a second. Those aren't fluxes that I looked at, but essentially we've got 900 petagrams in surface water, 37,000 in deep, and that thermohaline circulation, the movement of water, of carbon from shallow to deep, for example, is really important. And then there's another flux here that's from biota. We're going to talk about that in just a second. But those ocean fluxes, the movement of carbon from shallow to deep, is an important component of moving carbon to deeper water and storing it there. Now, we generally think of there being two different types of pumps for moving carbon to depth. The first is a biological pump, and that biological pump is essentially organic detritus and calcium carbonate skeletons that sink to deeper waters. So we've got NPP in our surface water, and that's going to sink and get into deeper water, not necessarily because of the movement of water from shallow to deep, but just long-term sinking of that organic matter. And that's one way that carbon gets from shallow to deep. The second is what's called the solubility pump. And this is when carbon becomes carbonate or is made soluble in water, and then it's pumped through movement of water from shallow to deep. And it's bottom water formation that transports a dissolved carbon to depth. So that carbon dissolves, for example, and then we know for thermohaline circulation, for example, when waters become cold and more salty because of evaporation, they tend to sink. And there's a couple points that we talked about with thermohaline circulation where water moves from shallow to deep and takes all of that dissolved carbon and brings it deep. On the other hand, we know as part of that thermohaline circulation is that we're going to have upwellings too. And there's upwellings that have dissolved carbon in them, and they are going to outgas that carbon also. So when we take a look at these fluxes and these pools, we can also calculate mean residence times, for example. So if we say that the atmosphere has somewhere on the order of 762 petagrams, we can look at all the fluxes going into it, and we can add up 91 plus 1 gives us 92, 96, 104, 160, let's say 162. And we can take a look at 162 as a fraction of 762. And that fraction is roughly, we'll say 5. So if you take a look at all the fluxes going into the atmosphere, and we know the size of the carbon into the atmosphere, the mean residence time of carbon in the atmosphere is about 5 years. If you go through the book, they'll say the mean residence time of carbon in the atmosphere is about 5 years. And that's how they get that number, is again thinking about the flux over the pool. And so in the previous example, we were able to get an estimate of what the mean residence time of carbon was in the atmosphere because we can break down those individual fluxes. The mean residence time of carbon in terrestrial plants is approximately 11 years. So for every cycle of carbon in plants, we're going to get 2 cycles in the atmosphere. So it's about 10 years or 11 years for carbon once it enters a plant to stay in there. The mean residence time of carbon in soil is even longer. It's 25 years. There's different pools of carbon in the soil, and some, that's just the mean residence time. Some carbon stays a very short time in soil, some much longer, but on average, if you take all the carbon in the soil and take a look at fluxes in and out, we're talking somewhere on the order of 25 years for the mean residence time. What's important besides all these individual pools and all these individual fluxes is to know that humans are now significant. If you look at the things that we do relative to the other fluxes that would have been present before, fires were always a natural component, but we've changed fire frequency. If you look at just fossil fuels, for example, we're talking somewhere on the order of 8 petagrams, and compare that to the amount of NPP, for example, or heterotrophic respiration. We're now, just our actions alone for burning fossil fuels is a significant component of the carbon budget. It's a lot bigger than other factors, for example, and it's significant globally. So 1%, the amount of carbon that we put into the atmosphere is approximately 1% of its entire pool. Humans are significant. And if you take a look at all the carbon that's being cycled and look at fossil fuels and land use, we get at the number of somewhere on the order of 15% of the carbon that's being cycled is associated with humans. And so we really have become a significant component of the global carbon cycle, numerically significant. Now, this is table 14.1, and what it is annual emissions and the fate of anthropogenic carbon. This is essentially what we had looked at before. The sources of the numbers might be a little bit different, but it gives you an estimate. Anthropogenic carbon sources, 9.1 petagrams of carbon per year. And again, that's 10 to the 15th grams of carbon per year. That's a big number. So 9 petagrams of carbon per year are what are thought of as being anthropogenic carbon sources. Fossil fuel emission and cement production is roughly 8 of those, 7.6. And again, it's mostly fossil fuel production. A small amount is cement production, but that's a factor that's pretty easy to calculate, so they're put in there together. And then land use change is 1.5 petagrams of carbon. So somewhere on the order of 7.6 petagrams is associated with fossil fuel, and that's the bulk of our anthropogenic carbon sources. Carbon sinks, we need to have a balance, and when we take a look at the repository of this carbon that's being put into the atmosphere, it has to balance with sinks. Storage in the atmosphere, 4.1 petagrams, oceanic uptake 2.2, terrestrial uptake 2.8. So actually, most of the carbon, somewhere on the order of half of the carbon that we're emitting into the atmosphere from fossil fuel production and land use change is being stored in that atmosphere, and it's accumulating. When we look at our CO2 concentrations, that's why we see our CO2 concentrations going up. Oceanic uptake and terrestrial uptake is the other half, roughly. And so we have a land sink, we have an ocean sink, where we're getting more storage than we are release currently. But about half of it is being stored in the atmosphere, and the other half goes into ocean and terrestrial sinks. Now, next what we're going to do is focus on the changes in the atmospheric CO2. And because this is a long-term repository of carbon, or has been, and we've seen changes in the pool size of this, we're going to think about what those changes have been and why they've increased.